We are currently at a point where not only new rockets are being tested, but a new class of space technology is also being developed. Nuclear energy in space, not as a source of fear, but as a practical tool. More energy for surface operations, more power for telescopes, and above all, propulsion systems that can radically shorten spacecraft transit times. If that works, missions will shift from being a logistical burden to repeatable, robust operations in deep space and to Mars. If it doesn't work, we'll stick with chemical propulsion, just like we have for half a century. But demonizing a technology from the start and refusing to research it just because certain ideologies demand it isn't the right thing to do either. Why push politics and strategy now? At the end of 2022, the United States administration explicitly made expanding dominance in space a strategic priority, with clear directives to treat space travel as a security and economic resource. That shifts priorities, budgets, and risk appetite. In this situation, nuclear concepts are suddenly no longer just research for the future, but candidates for demonstrations in this decade. My name is Serwin, and this is Mars Chronicles. First, let's get an overview so we don't misunderstand each other. Nuclear energy for surface power supply, in English fission surface power, these are the kilopower types. This is about nuclear fission. The idea is to place small, reliable reactor units on the Moon and Mars that provide constant energy for habitats, in situ resource utilization, smelting furnaces, and laser communication. National Aeronautics and Space Administration has demonstrated early fission systems with kilopower and kilopower reactor using Stirling technology and is further developing the concepts. These approaches carry a relatively low technical risk because they primarily provide stationary electrical energy, nuclear thermal propulsion, or nuclear thermal propulsion for short. The idea is that a nuclear reactor directly heats a propellant, for example hydrogen, and expels it. Much higher specific impulses, or specific impulse for short, are possible here compared to chemical engines. The practical result: significantly shorter transit times to Mars and stronger T-maneuvers for lunar missions. Defense Advanced Research Projects Agency and National Aeronautics and Space Administration are coordinating on demonstrators, for example Draco and related concepts, as an intermediate step toward operational capability. Nuclear thermal propulsion is technically demanding: materials, reactor cooling, and radiation protection. But the emission gains are highly relevant. Or rather, nuclear-powered electric propulsion, or in English, nuclear electric propulsion for short. Here's the idea. A nuclear reactor generates electricity, and this powers electric propulsion systems, whether it's Hall, ion, or variable specific impulse magnetoplasma rocket-like systems. Very high specific impulse, extremely efficient for long heavy transports like depots and other heavy freighters. The advantage: very good fuel efficiency. The disadvantage: large mass and radiological requirements plus thermal dissipation in a vacuum is tricky. The integration of refueling plus depots plus zero boil-off. Neither nuclear thermal propulsion nor nuclear electric propulsion replace the need for chemical propellants and for reliably storing them in orbital depots. In the medium term, we can't completely avoid chemistry. The combination of nuclear energy for cooling, pump systems, and thermal regulation, along with technical solutions for zero boil-off, will be a key requirement to make complex human landing system or Mars logistics chains operable at all. That all sounds nice, but what does it mean? Starship as a lunar lander doesn't just need engines, it needs an entire logistics chain. Tankers, depots, long-term storage, nuclear power acts as an enabler here, efficient cooling, active tank management, and possibly even stationary energy at orbital depots or gateway nodes. The Raptors may handle the thrust part, but energy and thermal management are a whole different dimension. Tests like the early Raptor descent burn clips answer engine questions, while nuclear systems answer the other question. Can we monitor, manage, and distribute fuel in space for extended periods? Or even take it a step further, can we sustainably produce fuel on other celestial bodies? Solar cells and batteries can certainly be part of the answer in the long term, but in the short to medium term, we will most likely not be able to avoid nuclear power. And at this point, it's worth taking a brief change of perspective back to Earth. Before we talk about nuclear propulsion, it's worth taking a look at something that already passes as alien technology today. And that's clearly the Raptor 3 engine from SPACEX. That's no longer a classic rocket engine. It's an extremely highly integrated system of combustion, cooling, material science, and manufacturing. Full flow stage combustion, extreme chamber pressures, regenerative cooling, and minimal tolerances. Things that sounded like science fiction 20 years ago. If you look at who's actually working in this field right now, you quickly realize that this is no longer some exotic fringe topic, but a coordinated large-scale project on multiple levels. On the government side, it's mainly National Aeronautics and Space Administration that's active. For years, they've been running programs like kilopower and fission surface power, reactors for energy supply on the surfaces of the Moon and Mars. In parallel, there are entire program lines within National Aeronautics and Space Administration and its research partners that deal with nuclear propulsion, both nuclear thermal propulsion and nuclear electric propulsion, especially with a focus on deep space missions and long-term transport architectures. On the military-industrial side, Defense Advanced Research Projects Agency is a central driving force. There are programs running there that explicitly aim to practically demonstrate nuclear propulsion systems in space, not just on paper, but as flight-ready hardware. The most well-known example is the Draco program, which, together with industry partners, aims to show that nuclear thermal propulsion systems in space are realistic, controllable, and above all, safe. Here too, it's less about science fiction and more about taking the first real step from theory to operational use. And then there's the industry. Companies like Westinghouse, BWXT, Northrop Grumman, General Atomic, and a whole range of specialized suppliers and startups are working on exactly the building blocks needed for this. Fuels, reactor cores, shielding, structural materials, miniaturization, and heat dissipation, these aren't glamorous topics, but that's exactly where it's decided whether nuclear spaceflight will eventually become a system or remain just a footnote. Of course, you can label problems as unsolvable and immediately put yourself in the loser's seat, or you can ask yourself how a problem can be solved. Above all, there is now a clear political framework. The White House has made it very clear with new directives that space travel, and especially nuclear space technology, is a strategic priority. That not only provides funding, but more importantly, something much more significant: time pressure and a new willingness. Not to postpone things until perfect conditions, but to actually build and test them. When you put all of this together, you get a pretty clear picture of how realistic the next steps are. In the short term, meaning in the next 3 to 6 years, the most likely successes won't be spectacular spaceships, but rather pretty down-to-earth things. Stationary reactors for power supply on the surfaces of the Moon and Mars in the range of kilopower, and technological demonstrators for cooling, long-term storage of propellants, and zero boil-off systems. These are the basics that absolutely have to be solved. In 5 to 10 years, real practical applications in cislunar space will likely become plausible. For example, nuclear-powered fuel depots, electric tugs for heavy loads, or permanent energy supply for larger infrastructure in lunar orbit and on the lunar surface. However, this assumes that politics and industry continue to pull together and don't hit the brakes at the first sign of resistance. In the long term, meaning beyond 10 years, things will get really interesting. Nuclear thermal propulsion systems for manned Mars missions to significantly reduce travel times, and nuclear electric propulsion for large transport fleets between Earth, the Moon, and Mars. Technologically, all of this is possible, but it's expensive, complicated in terms of regulations, and extremely sensitive politically. That's why such massive tasks shouldn't be left to stagnate or be handed over to the private sector, but should be researched and developed by space agencies like National Aeronautics and Space Administration and European Space Agency. And that brings us to the real risks, which are not technical in nature. The biggest issue is public perception, especially here in the German-speaking world. Nuclear technology in space immediately triggers old reflexes, fear, mistrust, and protests. That's why transparency, safety concepts, and comprehensible risk analyses will be at least as important as the technology itself. There's also the issue of accident scenarios. What happens during a rocket launch with nuclear payload if something goes wrong? What about an accident in orbit? These questions need to be answered not only technically, but also legally and politically. That needs to happen before this moves forward, not after. But if we leave all naivety aside, we can say with great certainty that at least some of the current nuclear superpowers already have various systems in orbit that carry nuclear warheads. And finally, there's the geopolitical dimension. If nuclear space energy and nuclear propulsion really become practical, they will fundamentally change power projection, logistics, and strategic reach in space. That's why these new directives and the political push exist. This topic won't disappear in the coming years. On the contrary, it will become increasingly central. For Mars, that doesn't mean 6 to 9 months of transfer time anymore, but rather 3 to 4. Some even talk about less than 40 days of transfer time to Mars, and that's not just a cosmetic difference. That not only halves the time the crew is exposed to cosmic radiation, it also massively simplifies supply, psychology, mission planning, and emergency options. Technically, however, nuclear thermal propulsion is anything but trivial. You have a reactor that reaches very high temperatures, you have hydrogen that is being pushed through this reactor structure, and you need materials that can withstand these temperatures. They must not become brittle or be corroded by the hydrogen or start to crumble radioactively. This is materials science at Champions League level. The United States of America already did exactly that in the 1960s with NERVA. It worked politically, but it was buried anyway. Today, the comeback of this idea is the Defense Advanced Research Projects Agency National Aeronautics and Space Administration program around Draco. The goal is to test a real nuclear thermal propulsion demonstrator in space in this decade. To clarify, these engines are not for rockets that launch from the Earth's surface. They are used in interplanetary and deep space. And here's the crucial point. Without powerful energy sources in space, there will be no scalable logistics. Solar panels become extremely heavy and impractical beyond a certain power level, while nuclear reactors are compact, long-lasting, and independent of sunlight. So especially when we're talking about the permanently shadowed craters at the moon's south pole in the context of Artemis, this becomes particularly interesting. Now comes the third component, which is often forgotten. Stationary reactors on the moon and Mars are not for propulsion, but for electricity. National Aeronautics and Space Administration has been working for years on kilopower and fission surface power. The idea is small, robust reactors in the range of 10 to 100 kilowatts. To supply habitats, operate in situ resource utilization facilities, produce fuel, power communication systems, and above all, supply cooling systems and cryo systems. This is the point where the circle closes with Starship. If you want to store fuel in orbit or on the moon for weeks or months, you need active cooling. Zero boil-off can't be achieved passively. That's an energy problem, and this is exactly where nuclear power suddenly becomes not just nice to have, but essential. What does that mean specifically for Starship and human landing system? Starship itself won't get a nuclear engine for 100 good reasons, but the entire architecture around it is screaming for energy. None of this will work without strong, reliable energy sources. Chemical engines solve the propulsion part, nuclear systems solve the infrastructure part, and that's exactly why these programs are running in parallel right now. The United States isn't building either Starship or nuclear. They're building both because they're solving two different problems. And this is exactly where the political dimension comes in. Whoever controls energy in space controls logistics, and whoever controls logistics controls presence. And while Germany is shutting down nuclear power plants, the rest of the world is building reactors for cheap electricity both on and off our planet. That means Germany is losing purchasing power, influence, and respect in the world, and it's dragging the entire European Union down with it. At the latest since the space directive from the White House, it's clear nuclear technology in space is no longer an exotic research topic in the United States, but strategic infrastructure. The document isn't about exploration, but quite openly about space superiority, that is, dominance, freedom of action, and deterrence in orbit and beyond. This is where the companies mentioned earlier come back into play. Because while National Aeronautics and Space Administration is supposed to spearhead these efforts, that doesn't mean they're doing it entirely on their own. They do award contracts to private industry. BWXT is particularly interesting because they build both civilian and military reactors and have a lot of experience with compact, highly reliable systems. In 2022 and 2023, National Aeronautics and Space Administration awarded several contracts to develop exactly these kinds of 40-kilowatt class reactors for the Moon. For Draco, which is a nuclear thermal propulsion, Lockheed Martin is on board as the main contractor with BWXT as the reactor supplier. So, what is realistic by 2030? You have to be brutally honest here. By the end of this decade, 3 things are realistic. A nuclear thermal propulsion demonstrator in space, it's probably going to be Draco. A one-time flight to show the reactor starts and runs, the engine ignites, and everything survives. 1 or more fission surface power demonstrators on the Moon. Not necessarily 100 kilowatts yet, but small, robust reactors that supply a few habitats and in-situ resource utilization experiments. Nuclear electric systems for unmanned logistics and deep space missions. Nuclear electric systems for unmanned logistics and deep space missions. Not huge freighters yet, but the first real practical applications, which most likely won't happen until after 2030. Nuclear-powered manned Mars spacecraft, huge nuclear freighter fleets, and fully developed nuclear lunar networks. That's more of a 2030s, 2040s timeframe, but the architectural decisions are being made now. China has long been openly working on its own nuclear spaceflight concepts on nuclear thermal propulsion, like propulsion systems, reactors for the Moon, and on a permanent lunar base together with Russia, the so-called International Lunar Research Station. China has a structural advantage here, significantly fewer political inhibitions when it comes to nuclear technology. While the United States has to send every reactor through multiple layers of safety checks, approval processes, and public relations debates, China can iterate more quickly. That's why the new United States directive is so clear. It's no longer a research race, it's about securing a position. Europe, on the other hand, is divided, while many European countries like France and Great Britain are going all in. Germany chose to step aside from nuclear energy and now criticizes others. Now comes the uncomfortable part. Nuclear systems in space are always dual use. A reactor that delivers 40 kilowatts to the Moon can just as easily power sensors, supply radar, feed communication nodes, and of course also support military infrastructure. A fast nuclear propulsion system for cislunar travel is valuable for more than just research. People in Washington, Beijing, and Moscow all know it, even if it's not spoken aloud. And Starship makes all of this possible, not because it is nuclear itself, but because it brings mass into space cheaply. Reactors, radiation shielding, radiators, and other infrastructure, all of that is heavy. And this exact weight was the killer argument against many of these concepts for decades. With Starship, this calculation changes fundamentally. Suddenly, it's realistic to bring several reactors to the Moon each year, to take large radiator surfaces along, to build redundant systems, and to design things not just to the limit, but to make them robust. You might find nuclear technology unappealing and be afraid of it, but you can't argue away physics. Without dense, reliable energy sources, there will be no real space economy. If you soberly consider Starship, moon bases, reactors, nuclear propulsion, and new spaceflight doctrines together, you quickly realize that we've reached a point where an expedition hobby is turning into infrastructure. The last 60 years have been characterized by a simple pattern. You fly somewhere and do something more or less impressive. And in the rarest of cases, you come back and almost start from scratch the next time. Apollo was the pinnacle of this model, technologically brilliant but structurally completely unsustainable. You can't build an industry with solar panels and batteries. You can't build an interplanetary infrastructure with chemical engines alone. And you can't establish a presence with one-off missions. The great irony is, the truly revolutionary things always look terribly unromantic at first. A reactor on the moon isn't a flag-planting moment. A nuclear tug between Earth orbit and the moon isn't an epic tale of heroism. Without these things, everything else is just a flash in the pan. And this is where the geopolitical level comes back in. The United States, China, and potentially other powers are currently building up positions, logistics, reach, and autonomy. Of course, not everything will work out and there will be setbacks. The first reactors will have problems, the first nuclear drives will be delayed, and architectures will have to be redesigned, but the sails are set. Just like the railroad didn't come because people wanted to travel romantically, or electricity didn't come because light bulbs are so pretty. That's how nuclear infrastructure will come to space. Not because it sounds cool, but because it's economically and physically logical. At least as long as we don't have any other groundbreaking energy technology yet. And that brings us to a point that we can state clearly. The next 20 to 30 years of space travel will change fundamentally more than the last 50. If you were able to take something away from this video, then subscribe and let me know in the comments what you learned about Atom, whether on Earth or in space. My name is Serwan, and this was Mars Chronicles. Thanks for tuning in. Per aspera ad astra. Ad astra.